Magnesium is the 12th element in the periodic table with atomic number 12. It is a shiny gray metal and belongs to the alkaline earth metals group. Magnesium is the 8th most abundant element in Earth's crust, making up about 2% by weight. It is also found in significant quantities in seawater, where it exists primarily as dissolved magnesium ions. Like other reactive metals, magnesium does not occur naturally in its elemental form. Instead, it is found in mineral compounds such as dolomite, magnesite, and carnallite. Magnesium stands out due to its low density, which is approximately 1.74 grams per cubic centimeter, significantly lighter than aluminium, and about 2/3 the density of aluminium. This lightweight, combined with good mechanical properties, makes magnesium and its alloys valuable in applications where reducing weight is crucial. Despite its lightness, pure magnesium is relatively soft and not particularly strong, but when alloyed with other elements such as aluminium, zinc, or rare earth metals, it becomes much more structurally useful. One of magnesium's key features is its excellent strength-to-weight ratio. This makes it highly attractive in industries where both mechanical performance and lightness are critical. In addition, magnesium has good damping capacity, meaning it is effective at absorbing vibrations and shocks, which is useful in automotive and aerospace components. However, it is more reactive than aluminium and less corrosion-resistant in its pure form. To mitigate this, surface treatments and protective coatings are often used when magnesium is deployed in environments prone to moisture and salt exposure. Magnesium is also notable for its role in pyrotechnics and incendiary devices due to its flammability. When ignited, magnesium burns with an intense white flame and releases a large amount of heat, making it useful for flares, fireworks, and military applications. This characteristic also means that magnesium must be handled carefully during manufacturing and machining processes to prevent accidental ignition. The production of magnesium typically involves two main methods: thermal reduction and electrolytic processes. The thermal method, known as the pigeon process, is widely used in countries like China and involves the reduction of magnesium oxide using ferrosilicon in a vacuum. This method is relatively low-tech and energy-intensive, but economically viable in areas with low labor costs and abundant raw materials. The alternative is the electrolytic method, where magnesium chloride is extracted from brines or seawater, dehydrated, and then electrolyzed in molten form. This process requires high energy input and is typically located near sources of inexpensive electricity, similar to aluminium smelting. Magnesium is recyclable, although its recycling rate is lower compared to aluminium. One reason for this is that magnesium is often used in small quantities in complex products. Nonetheless, recycling magnesium can significantly reduce the environmental footprint associated with its production, particularly in reducing CO2 emissions. Magnesium's applications span a wide range of industries. In the automotive sector, magnesium alloys are used for components such as steering wheels, engine blocks, gear housings, and transmission cases. By replacing heavier metals with magnesium, car manufacturers can reduce the overall vehicle weight, which improves fuel efficiency and performance. In aerospace, the high strength-to-weight ratio of magnesium alloys is advantageous for constructing structural components, though their use is limited by flammability concerns. In the electronics industry, magnesium is used for producing lightweight laptop frames, camera bodies, and mobile device casings. Its low density and good machinability make it suitable for precision parts that require both structural integrity and minimal weight. Magnesium is also used in sporting goods such as bicycle frames, tennis rackets, and climbing equipment, where performance and lightweight construction are critical. Magnesium compounds have important industrial and medical uses. Magnesium oxide, MgO, is used in refractory materials, such as furnace linings, due to its high melting point and chemical stability. Magnesium hydroxide is a common ingredient in antacids and laxatives. Magnesium sulfate, known as Epsom salt, is used in agriculture, medicine, and bath products. In the steel industry, magnesium is used to remove sulfur during the refining process, and in aluminum production it serves as an alloying element to improve strength. Biologically, magnesium is essential to all living cells and plays a vital role in many physiological functions. It is a key component of chlorophyll, the molecule responsible for photosynthesis in plants. In humans and animals, magnesium is required for hundreds of enzymatic reactions, including those involved in muscle contraction, nerve transmission, energy production, and bone development. Dietary magnesium is found in foods like leafy green vegetables, nuts, seeds, and whole grains. Magnesium deficiency can lead to muscle cramps, fatigue, and cardiovascular issues, while excessive intake, usually from supplements, can result in gastrointestinal disturbances. Environmental concerns associated with magnesium production primarily stem from the energy-intensive nature of its extraction processes. The pigeon process, for instance, generates significant carbon dioxide emissions due to the use of coal or coke as a heat source and reducing agent. Additionally, mining and processing of dolomite and magnesite can result in habitat disruption and pollution if not properly managed. There is growing interest in developing cleaner and more efficient production methods, such as using renewable electricity for electrolysis and exploring new reduction techniques with lower carbon footprints. To address environmental and sustainability concerns, researchers and industry stakeholders are investing in improving the life cycle management of magnesium products. This includes designing for recyclability, improving collection and sorting of magnesium-containing materials, and optimizing processing methods to reduce waste and emissions. The Magnesium Stewardship Council and similar initiatives are working to promote responsible sourcing and sustainable production practices. Magnesium is also being studied for its role in emerging technologies. One example is magnesium-ion batteries, which aim to provide an alternative to lithium-ion batteries. These batteries potentially offer advantages in terms of energy density, safety, and cost, although they are still in the research and development stage. Magnesium is also being explored as a material for biodegradable implants in biomedical applications. Since magnesium is biocompatible and dissolves in the body over time, it can be used for temporary support structures such as bone screws and stents, eliminating the need for secondary surgeries to remove implants. Magnesium's unique combination of low weight, good mechanical properties, essential biological role, and recyclability make it an important material in both industrial and biological contexts. While challenges remain in terms of corrosion resistance and environmental impact during production, its potential for use in lightweight structures, energy storage, and medical technologies positions magnesium as a valuable element for the future. With advancements in alloy development, recycling infrastructure, and cleaner production methods, magnesium is likely to see broader adoption in sustainable engineering and high-performance applications.